Toby face.
Yeah.
Yeah. There's your meeting ID was 84.
445573-3366.
What's your go up a little bit? It's the meeting ID.
Yeah.
Oh, that is.
That is
And
a
then
meeting
is there a password?
ID.
Or do you just that's all you need?
I think that's all you need.
Oh, okay. There's no passcode. Okay. Let me see if I can get in there with my phone.
Yeah, I think the passcode is for administrative.
Okay.
Testing. Okay, we got feedback.
Hey, Tom, are you on? Or Ramiro, or who's on? Anybody?
I'm on, Liz.
Ramiro?
Yes.
Okay, I'm gonna change your name to say Ramiro. So, or do you want? Can you change your name to say Ramiro?
Oh, where are you seeing that?
It's got my name on both little ICC logos.
Oh, really?
Yeah.
Because yeah, that'd be good if you can do that.
I don't think I can do it because I'm not the host. You're the host right now.
Okay.
So if you just put your, if you put your in the little square that says that is you under host.
Okay.
Go like if you were going to mute your microphone, and then there's three little dots next to the mute on the participant list. Do you see the participant list?
Yes.
Then you see the mute button.
Here's the
Just
participant
hover
list.
over your name. Here, let me do this real quick. I'll give you the host back.
Yeah, I don't see
Are
my
you at
name.
the top?
Oh, there you go.
Hold on here.
Is that her? Oh, this is you.
There,
Okay, so you want me to change this?
I just changed it. Let me make you host again. Hold on.
Oh, you just changed it. Okay.
Yeah. I'll make you host again.
Okay. Thank you.
And then can you make me co-host?
Okay. How would I do that?
So the same way. So if you go on the participant list where it says my name, and then it has the blue mute button next to it, there's three dots. If you click on that, you should be able to say make co-host.
Okay, I'm just trying to. Why is it? It's only showing me. Let's see. Oh, here we go. Make co-host. There you go. Are you co-host now?
Yes.
All right. Cool.
That way I can switch them quickly.
Okay.
We still have how much time? Half an hour?
Yeah, 25
Half
minutes.
hour.
I'm gonna leave.
All right, well, I'll just be in the background if you guys need me, okay?
All right. Thank you. I wasn't sure what she was talking about.
Oh,
It
that's
was
right.
on the participants. Okay.
Just so you guys know, there's 127 registered.
Cool.
Very nice. Thank you, Liz.
Tell these guys.
Alrighty. And are you two the only panelists? Lisa, are you gonna do it from his computer, or are you guys doing it onto different devices?
Liz, I'm doing it from my laptop.
Oh, okay. Sorry, I just assumed Lisa was there.
Lisa is she went to
On
grab a
site.
bite to eat. Yeah,
Oh, okay.
but she'll be back. She's gonna monitor it from the attendee side too.
Okay. All right. Good afternoon, everyone, and welcome to Pipe Sizing. Why is it important? Your instructors today are Ramiro Mata and Lisa Reiheld of the ICC-PMG Technical Resources team. Just a few housekeeping notes before I hand it over to Ramiro and Lisa. Please be sure that your mic is on mute throughout the duration of the program. If you have a question or comment, please reserve it for the end panel discussion. If you lose connection, please join us again. We will admit you in the waiting room. And the CEUs will be marked complete upon the end of the event. And you should see it in your ICC Learning Center account within 24 hours. With that being said, I will go ahead and hand it over to Ramiro and Lisa. Thank you.
All right. Thank you very much, President Richardson. We're happy to be here. Thank you for the opportunity to speak to the group today. This session is going to be a hybrid section. So there's going to session. So there are people online also participating, as well as you guys here. With me is Lisa Reiheld. She'll be co-presenting. So we'll kind of take turns on. I'm sorry. So we are recording this as well for future use. So just a little bit about. Also, we have another colleague here, Tom Roberts. He will be providing backup from online as well. And I think Gary Gauthier is also here. Okay. So just a little bit of introduction about myself. I've been in the codes and standards realm for about 15 years. Started out in testing plumbing products at CSA Group. So we used some of the standards, the plumbing standards, and actually I was running the tests on those and certified those. And I got involved in developing standards because some of them, some sections actually required some improvements. And all of you are, I didn't know this at the time, but anyone here can participate in developing standards if you want. If you see a standard or a code even that you feel requires changes, you can submit proposals for that to make the changes. So I'm here with Lisa Reiheld, who I worked with at one of those at the plumbing lab. We were testing plumbing products at that lab, at the CSA lab in up near Cleveland. Lisa is a director in the PMG Technical Resources team. So her and Gary Gauthier and other colleagues here, there's 5 of them that do pretty much split up the country doing code training for folks like yourself. And I was hired on about a year ago to help develop standards that we're going to be talking about later on in this presentation. And then the newest staff member we have is Tom Roberts. He was formerly with the Australian Building Codes Board, so he's got a perspective on codes and standards outside the U.S. So since ICC is becoming more involved with codes in other countries, he was a great addition to the staff. We're led by Matt Sigler, who's also another plumbing veteran. He and I worked on many standards together, developing standards. So I guess this is just some housekeeping items that any reproduction of this presentation is you need to get approval from ICC if you want to record it. This is the QR code to sign in if you would like to get credit for this session. So I'm going to leave it there for ICC, yes. So there's the alternate sign-in method there at the bottom. You'll see that website there, iccsafe.org/attend. So I'm told that you have to sign in using this website or the code, and then you have to also sign back out. There's a QR code that we'll show you at the end to be able to sign up. And it says 2 weeks. You'll get 2 weeks, allow 2 weeks to get credits for this session. And then here's another QR code. This one is for submitting questions. We're going to have a panel discussion in the second half of this session. The actual experts at pipe sizing and research that we're doing. So I'm not the expert on this. My expertise is more on the testing side and the standards development side. So at the second half of this session, we're going to have 3 panelists that are on our committee, standard development committee. Actually, Terry Hahn is also on our committee, so he is devoted 4 hours every month to attend our meetings. Thank you for that, Terry. So if you'd like to submit questions, you can scan this code, and it'll take you right to a website. You can enter your question, and then we'll have a list of that, and you'll see the list of questions also when you submit. When you get on that website, you'll see all the questions that others have submitted already. So, if you have the same question, you might not want to submit another one. If you can also use this website at the bottom there, but if you use the website instead of the QR code, you have to enter this that string of numbers there on the second to last So this is what we're going to be discussing today. We're going to go through a brief history of plumbing systems. Modern plumbing systems, you might say we're not going back to the Roman times. But and then we're going to talk about, what factors actually are, driving this need for proper pipe sizing. And then we're going to go through the unintended consequences of having the pipe sizing methods that we have right now that people are using to design systems. And then after that, we're going to go through the pipe sizing methods that are out there that other countries are using to try to size their pipes better. And you'll see that based on I'll show you some graphs that shows you what the actual use is on a building and versus the predicted use. And it was pretty shocking when you see that. So after that, we're going to talk about the leading researcher that we're working with at the University of Miami, Dr. Andiroglu, will be going through the fifth section there on what they're doing as far as their research to develop this new standard. So ICC 815 is a standard that we're developing for pipe sizing, but it's a standard that covers not just the supply system, but it also will cover the drain side and also the vent side. So the venting system, the drain system, and the supply system. So the entire plumbing system will be in the scope of this standard. And then the second half will be the last item there, the panel discussion, where our panel will be able to dig a little bit deeper into some of the topics that we cover, and you'll be able to get more details on, if you have questions on anything that we cover. So, we'll dive right into the brief history of modern plumbing systems. Like I said, Lisa Reiheld and I, and most of you probably met her yesterday at the marking and labeling session, where she valiantly presented, even with her losing her voice. But we'll see how she does today. Hopefully, yes. So, Lisa.
Good afternoon, everyone. I'm happy to be here. Still have the frog in the throat here, but I will do my best to get through this. So I am going to discuss some of the brief history of modern plumbing systems, just to kind of give a background of where we've come from and where we're going, mostly where we've been, I guess. So the first water distribution systems were in Schaefferstown and Bethlehem, Pennsylvania. And those go back as far as 1746 and 1754. So that's, just shy of 300 years ago. But, those were the initial water distribution systems that were put in place. So that's where it came early on. And Philadelphia actually developed the distribution system using some horse-powered pumps, literally horse-powered. And then the first sand filtration plant was in Richmond, Virginia in 1832. And the first steam-powered pumps were actually in Chicago in the mid-1860s. So those have been around about 250 years or so. All right. Some other key milestones to the history. In the UK in 1848, there was a Public Health Act, and this influenced the development of sanitary waste systems. And so not only the clean water coming in, but the waste needed to go out, because just because you bring clean water in, you're not living in a sanitary condition if you don't have something to do with the waste as well. And then in 1866, New York put in a comprehensive sanitary code, conditions for urban areas, because obviously when you're in a more populated area, you have a bigger problem with sanitary conditions so that you don't have any disease, that kind of thing. Before becoming the 31st president, Herbert Hoover, who was a civil engineer by trade, he created the National Bureau of Standards, or NBS for short. And within that National Bureau of Standards, there was a plumbing code developed that was actually called the Hoover Code. And then, yeah, so that was published in the 1920s, before he was president. So just to give a little insight into the Hoover codes, he appointed a civil, Harding, President Harding at the time, appointed a civil engineer, Herbert Hoover, who would go on to become president, but he became the Secretary of Commerce, and that's how he became involved in the codes. And Hoover wanted to make sure that there was water, electricity in every home, as well as the indoor plumbing. So those were all important things and goals. So slightly different than the candidates that we have today for president and what they're looking for. So quite different. And at the time in the US, there was only 1% of the homes that had indoor plumbing. So this goal was quite robust in the fact that, you know, he was looking for it to increase from 1% to 99%. So in this Hoover Code that was called BH13, the title of it was Recommended Minimum Requirements for Plumbing. And it was basically codes, regulations, what we would think of today as standards, probably that covered all aspects of the plumbing. It covered what materials, allowable pipe materials, what the slope needed to be, how the fixtures were to be installed, maximum lengths of the plumbing. And this was actually codified in the 1920s. All right, here in this image, you see what might have been a typical 1940s, 1950s bathroom. Anybody ever been into a bathroom that looks like this before? Okay. Kind of familiar. I think we've probably all been there, but Roy Hunter was a researcher at the NBS, National Bureau of Standards at the time, and he developed some demand curves, guessing what the probability of use of water and the fixtures in the home would be. And he started his work in the early 1920s, and then he finally published his work in the 1940 publication. So if we've heard of the Hunter curve and what's still commonly used today as a reference for coming up with pipe sizes, this was published in 1940, but it was actually developed in the 1920s. And I think we would all agree, since it's been 100 years since the 1920s, that the fixtures and the amount of flow and the number of fixtures we have, all that kind of thing, has changed considerably in that amount of time. Where in that time period, we probably, you know, had a 3-bedroom house, no more than 1 bathroom. And now we have, you know, 4 and 5 bedroom houses that probably have 3 or 4 bathrooms in them as well. So he used limited building patterns, did some research, and he presented the load producing values of different types of plumbing fixtures and what load that would put on the system. And from that, he developed some curves that estimated the number of fixtures that are most likely to be operating simultaneously as the total number of fixtures in the design. And I think most of us agree that it was an overestimation of how they would be used. And additionally, today we have certainly the flow of the plumbing fixtures has certainly been reduced since when he did this research. So he did establish piping size for both water supply and drain discharge. I think we most commonly think of the drain or the pipe sizing for the water supply, not so much the drainage, but he did both. All right, so his work has helped designers to determine what the expected maximum flow needs to be in a building's plumbing system. It gives you a relationship between a number that's called a fixture unit. So that kind of normalizes everything into, a sink or a faucet, toilet is equal to this many fixture units, and it tells you within the building what the maximum flow rate would be in fixture units. And here's a definition: is a unit measure that estimates the water load that a fixture would put on a plumbing system based on its flow rate and frequency of use. The curves incorporate the probability of use of each fixture. So he was also making a guess of how often each of those fixtures would be used in an average home. This is an example here. This photo is of an early Hunter's curve, and just shows the fixture units that would be expected. And then a table here. This is actually from Appendix E of the 2024 IPC. That is the load values assigned to fixtures, converted to drain fixture units. So you can see in the far right-hand columns there, cold water, hot water, and total drain fixture units. And these numbers are coming from the Hunter's curve. All right. Once again, as we go along, we'll take the questions in the second half when we're having the panel discussion, and we'll monitor these questions. But if you want to use your phone, put it up to this, scan this QR code, and that puts you into the forum where you could type and ask a question, and we'll review those in the panel time. But that's just an additional one. So I'll let Ramiro take that forward.
Thanks, Lisa. Right now we're into section 2. So what are some of the factors that is driving the need for right sizing of pipes? So the first one is changing the water consumption. So you're all familiar with how good showers used to be back in the day. You get all kinds of water flowing over you, and now it's quite a bit different, right? And you can see in this image how much the flushing volume has changed from the for toilet. Another factor, and Dan could speak upon this, is the water quality. As the consumption has changed, it affects the water quality, which really no one really thought of. Everyone was just thinking about how do we save more water, and it was driven by drought, and especially out west. Where I'm from, I grew up in Cleveland, so we have plenty of water from the lake and from the sky. So and then the other factor is having this change. And as you all know, if you change one thing in a system, it affects the other systems. You can't just make a change in one part of the system and expect it to not affect others. So this table was borrowed from the Drainline Transport of Solid Waste in Buildings study. It's a report by John Keller and Pete DeMarco, where they studied water consumption, and you can see there the drastic changes that have occurred since 1980, between 1980 and 2017. The most, and you could see the urinals there, 96% reduction. from 1.5 gallons per flush to 1/8 of a gallon. So before the early 1990s, in the US, typical flush toilets were required 3.5 to 5 gallons per flush. And they used, float valves that were often leaky and so wasted a lot of water. The Energy Policy Act of 1992 reduced the maximum allowable flush for toilets to 1.6 gallons per flush. Because of these significant reductions in consumption, water began to age in the pipes. Because the pipes were still the same size, the only thing changed was the faucets and the shower heads. So you're not getting as much water flowing through the pipes. So they're staying in the pipes. Like a building like this, if they change all the shower heads and all the toilets, all the urinals to these modern rates, then the water is not flowing as much as it used to, so it stays in the pipes. So a lot of times, and we talked about the water quality, the disinfectants that the water plants add to the water dissipates while they're sitting in the pipes. And talk about water quality. The Safe Drinking Water Act of 1974 was established to protect the water quality of drinking water in the U.S. But focused on waters intended for drinking, whether the source was above or below ground. In 1989, NSF developed the NSF 61, which is the drinking water system components. It was published in 1989. So it was established to set requirements for contaminants directly imparted to drinking water from products, components, and materials used in potable water systems. So this applies to all finished products and all of the wetted components in the potable water system. So earlier I said that I was testing plumbing products. So they not only have to meet the performance, minimum performance requirements in the standard, but they also, if it's a faucet, a kitchen faucet or a lavatory faucet, they also have to pass the NSF 61 requirements, which means that it's a completely different test. What they do is they keep water intentionally in these plumbing fixtures, and they wait to see what leaches out of the materials that the faucet is made of. So, I mean, even then, the materials that you make the faucet out of has to be individually certified and must pass the NSF 61. So if you use any plastic components or any metals or anything like that, or even grease or anything, lubricants, they all have to have, they all must pass this toxicity testing. So a lot of us, before I was in this, just took for granted that, your faucet doesn't kill you, but it doesn't, because they have to pass this test. So the other factor that we spoke about was the drain and vent system performance. Without, as you all know, without properly operating drain, waste, and vent system, fluoride gases are released into the occupant space. So there's a couple of researchers at the National Bureau of Standards that assume that the relationship between static air and the drainage stacks were within the drain stacks were equal regardless of the height. Right? It was later found that in tall stacks, it was significantly greater than that of the drainage flow. So the airflow was actually significantly greater than the drainage flow. So researchers there's a lot of actually we just learned this, that there's a lot of research going on outside the U.S. for drains and we're trying to get work with them more because they're doing a lot of this research outside the U.S. So researchers in Scotland developed a mathematical relationship between linking drainage flow and airflow in drain stacks. And they're developing a model so designers can use that to properly size that. We actually had a chance to visit, I was telling Dan, we had a chance to visit drainage laboratory in the UK that was initially, this structure was initially built to test elevators. They turned it into a drain laboratory so they can test different configurations of drain systems, especially for high-rise buildings. So, because there's a lot of residences that are, especially in Europe, where they don't have any room, they have to go vertical. So, but there's not been any research done on that. People just, they use the existing design methods for tall buildings, the same methods they use for maybe a short, a 3 or 4 story building. So, and actually there's issues that come with that, and really super tall buildings like in Dubai, where that super Burj Al Khalifa building, which is I think one of the tallest buildings out there. They have issues with traps being blown out of toilets, and or traps being having negative pressure, and because the drain, the water in the drain actually approaches the terminal velocity, a couple hundred miles an hour going down, because they're going down so far. Yeah. So we're going to be working with them on that. So this is a graph that shows the relationship between airflow and drainage flow from Heriot-Watt University is in Scotland. Again, this is a illustration of you're all familiar with the trap, and the venting systems must be designed to maintain air pressure variation to within 1 inch of water column in order to preserve these trap seals. And we all know what can happen if that seal is not there. Again, this another reminder, if you joined us late, again, if you're online and you joined us late, please go ahead and scan this QR code, or if you're here, so you can enter questions. And with this section, we're going to go into the unintended consequences of modern flow rates with the current pipe sizes that we have.
Thank you. Yeah, so we're going to talk a little bit about the unintended consequences. We all know with every good idea comes some unintended things. We thought it was a good idea, but ultimately, maybe there's some things we didn't think of or consider that would become issues with the improvements that we made. So basically, when we have low water consumption with our low flow fixtures, some of the things that we experience in the water supply system are things like an increase in water age. So if you have the same size pipes, but you have less water coming out of each fixture, then that means the water that's sitting in your pipes between your supply and your outlet is going to be there longer. With the longer amount of time you have in there, the more chance you have for bacteria or anything along those lines to develop, so it becomes a problem. It also decreases the velocity at which the water is going through those pipes, which means with a decreased velocity, you're gonna not be scrubbing the inside of those pipes, and there's gonna be film that builds up in those pipes over time. If you do have disinfectant in the system, the longer it sits there, because you have less water going in that, the effectiveness of that disinfectant is going to dissipate before you actually get to use it, so that becomes a problem. Talked a little bit already about they're going to have a likelihood of pathogen growth because you're not turning the water over as fast. You don't have as many turns on the water when you have less consumption, but you have the same pipe sizes. It also increases energy use because, you know, you might be letting your water run longer to get the hot water to the outlet because you have less water coming out the faucet. Takes more time for the hot water to get there if you want to use it hot water to wash your hands or wash your face. So it actually might increase energy consumption in that way. On the sanitary side of things, you would have a shallower water depth in horizontal drains, which means you're going to have material building up there and might kind of get backed up or build up more quickly because you have a lot less water flow going there. And you have that, of course, leads to increased likelihood of blockages within your drainage system. And then in the vent system, you're going to have unnecessary piping due to the airflow capacity in horizontal drains. So there's really impacts onto all three of these: water supply, drainage, and venting, because you are using the same size water supply, drainage, and venting that you were using previously when you were using much more water. All right, this picture is a fun little graphic. We'll keep it PG and call it the boats in the canal here. But this is a cross section of your drain pipes and different stages here. So the picture on the far left shows in the 1940s, we'll say that the pipeline or the drain pipe was about half full of water, as well as some solid waste going down there. But you can see that at the top there was room for airflow, you know, because you have to have the airflow to go with it. And then in today's modern systems, because we're using less water out of the fixtures, we still have the same size drain pipe. We still have the same amount of waste going in that drain pipe, but the level of the water in that drain pipe is a lot less. So you have what I just said on the previous slide about you're going to have a greater chance for the solids in there to build up and not go anywhere because you have a lot less water in there, getting rid of the same amount of waste. I believe the waste is still a constant factor that hasn't changed over time. So anyway. All right, and then on the right, we have a scenario of what we may be looking at in the future, where we can actually reduce the size of the sanitary drainage to what you see there, still with the required airflow that you need to get it out. There'll be less water, but you have a lot less water in a smaller pipe, and then you might have two drainage lines, one that's carrying the black water waste and one that's carrying the gray water, because the gray water could potentially be treated and returned to use for specific appliances or fixtures that could use the gray water rather than just letting that go down the drain. All right, that's my sections. I'm going to toss it back over to Ramiro.
So earlier we mentioned that there are other pipe sizing methods that's in use around the world. So first, there are three systems, like what we said earlier. So there's a water supply. We're going to cover sanitary drains and sanitary venting. So each one of these, there's pipe sizing methods we can talk about. Oh, having trouble changing it. Okay, here we go. So with the research that's being done by the team at the University of Miami, so the first phase of the research was to do a literature review to see, you know, what is out there right now that's deals with pipe sizing. It's again, I mentioned earlier, it's led by Dr. Andiroglu, and Drew Rich is our PhD student that's helping along with this. They found over 20 methods of pipe sizing in use around the world. Yeah, there's no way. You know, those are all. None of these are. Most of these are new to us. So here's a graph that's showing several of the peak demand graphs or curves. So these are currently each one of these colors is a different method of estimating peak demand. So there's the peak demand method for the UPC. And then there's the IPC. And there's the Australian code. And there's the water demand calculator. So this was actually this graph was developed by Deakin University in Australia. They're also doing research on this because you know, water consumption is a very important aspect in Australia. They have a lot of arid areas there. So they wanted to show how, they wanted to see how the Australian peak demand curve compared to the other curves. In the Australian research, you can see in this bar graph here, the red bar is the Australian predicted peak demand. So they did research on 4 apartment buildings, and the red bars, their peak demand predicted method, and the yellow bar is the actual use, flow rate use. You can see that it's the predicted demand is way higher than the actual use. A similar study was done here in the US. It was funded by the California Public Utilities Commission. They compared Appendix A in the California Plumbing Code, which is the red dots there. That's the predicted demand for, on the bottom there, you'll see these are all residences, buildings. The predicted demand is the red dots. The blue dot is the water demand calculator, and then the black dot is the actual measured data. So there's a huge disparity in especially when you compare to the peak demand in Appendix A of the California Plumbing Code. And this is just a snapshot of the current pipe sizing method in the 2024 IPC. It does allow, in Chapter 6, it does allow design professionals to choose a method of pipe sizing as long as it conforms to accepted engineering practices. And that's, there's definitions for that. It also provides an option to use Appendix E to determine the size of branch mains and risers. And this is one from the UPC. This is the pipe sizing methods for the sanitary drain systems. This EN 12056 is one that's adopted by many, or it says 7 European countries. And there's more there. The ASNZS is the Australia and New Zealand standard. And in the last two, there's the IPC UPC. And then finally, there's other methods there from China, Denmark, and Japan. Again, a snapshot of the IPC's drainage method. And one from the UPC again. Okay, now we're moving on to the third system in the building, the sanitary venting. So they've not found, the researchers have not found very many pipe sizing methods for sanitary venting. But again, as I mentioned, there is research in progress to develop one that's applicable to modern flow rates. So the current sizing, for vents is based on approximate methods, assumed relationships to the drainage flow. And it's based on outdated airflow theory from the National Bureau of Standards. So this is, again, from the 2024 IPC section 906, table 906.1, and it talks about sizing of vents and vent stacks. And again, a comparable one on the UPC side. So again, to summarize, why we're looking at this and why we're developing ICC 815 is because current pipe sizing methods are not appropriate for the flow rates that we have today with the modern flow rates. And we have to address this because there's a real serious issue with pathogen growth within the piping system. Oops. And we need to have a system that works together on both the supply side and the sanitary drain and vent side. And properly sizing the pipes will also decrease energy use, because again, you don't have to wait to run your faucet to wait for the hot water to get there if it's sized properly. I guess so. We're going to go into the next section would be the development of the ICC 815 standard, and Dr. Andiroglu will be talking about some of the research that they've done so far. So this, ICC is developing the standards, in a new way, because we are actually doing research to go along with the development of the standard. So most standards are not done that way. You just pretty much you get a group of experts together and you develop, you develop requirements that you think, make sense for that whatever it is, product or system that you're addressing. So, but ICC decided, we're gonna do this with the help of researchers and get it, base the development of the standard on some actual real data. So the second phase of the first phase was literature gathering. The second phase would be actually testing some of these methods out. And I'm going to let Dr. Andiroglu provide some of that detail for you. Dr. Andiroglu, are you online?
Yes, good afternoon, everyone. Pleasure to be in this discussion this afternoon.
I'm going to go ahead and I'll switch slides when you tell me, Dr. Andiroglu.
Sure. So I think what Lisa and Ramiro has really ran us through so far this afternoon has clarified and hopefully signified the need, why we're doing this. And as part of the effort, the technical committee that was formed as part of the 815 Standard Development Committee effort represents expertise across the globe, really, from various sectors, including industry, regulatory agencies, designers, manufacturers, piping manufacturers. So collectively, we feel that the research that we are carrying through, coupled with the feedback of this faceted expertise brought on by the technical committee, will deliver the right response in this effort. You heard already the adverse impacts of improperly sized piping as a result of reduced flow rates. And we do want to continue with the reduced flow rates because we're all very much aware of the water crises that are, we're facing globally, further compounded by the climate change impacts across the globe. So as that happens, this dilemma is only going to get more highlighted and more complex. We have discovered through the literature review phase that not one answer may be the right response to all the pipe sizing needs in different regions of the world, facing these different challenges. So from the information we gathered through that literature review phase, now during the phase 2 of the project, we are on the way to establishing what may be the factors or parameters that may further be implemented as adjustments into demand estimations, the peak demand conditions, governed by various unforeseen contributors. And I'm going to name a few. For example, the cultural practices or hygienic practices in different regions may be contributing to how peak demand is established. So we are documenting data, collecting data that can help exemplify some of these factors that may contribute to peak demand conditions. And at the moment, much of the available data exists at a very low resolution. In other words, data that may be collected once a month as peak consumption rates, or at best, in some instances, hourly consumption data. However, it does not provide a true insight into the peak demand conditions on an instantaneous level. So our mission is to collect new data that is at very high resolution and translate such data into training sets for translating low resolution data into high resolution data, where we can then apply this concept across the globe in different regions to better understand the consumption, peak consumption patterns, and based on that understanding, develop the pipe sizing. Supply sizing versus waste and vent pipe sizing, we feel should be considered independently, but yet directly connected. One will feed into the other one. However, the factors we may develop, for example, for one may not necessarily apply in one of the other system types. So there is still quite a bit of work ahead of us on this topic, but one of the reasons we are taking this research-informed approach is really because we want to make sure that the new standard 815 that is developed remains as a viable living standard for generations to come, for decades ahead, and does not become obsolete as water use and consumption practices change in the decades ahead. One of the changes we're anticipating, for example, is supply water streams. We have already mentioned about the water scarcity challenges experienced across the globe. A little while ago, Lisa talked about, for example, the gray water and black waste collection streams. And as we implement more and more of these practices, gray water collection systems, or rainwater harvesting, for example, for use as supply water streams. Ramiro also mentioned about the water quality impacts and what happens in the piping, or the flow that comes out, and how does that impact the public health. So in order to better address all of these impacts and how pipes may be sized, even when we are looking at different supply streams, whether it's harvested rainwater versus harvested gray water, there's quite a bit of work ahead of us. So the research-informed aspect of the sizing guidelines will be focusing on these variations. And again, with the mission that what we develop remains as a living document, and it becomes adaptable by various communities across the globe in the decades ahead. You may forward, Ramiro, to the next. So, again, our approach, this research-informed and further strengthened by feedback from the guiding technical committee. First, we wanted to really establish a common vocabulary, even across regions, across different countries, so that we're all speaking about the same topic and relating to it the same way, especially later on as we discover the various parameters that may be contributing to this effort. So, the definition phase basically was establishing just that. Then, we moved on to through the literature review, the 20-some sizing methodologies that Ramiro listed on one of the slides a little while ago, that talked about who is doing what across the globe and why. And so from there, we're kind of in the middle right now, where we are focusing on the takeaways and from all this investigation, analyzing and synthesizing data, but existing data that we're gaining access to through collaboration from various regions and participating members, as well as new data that we are collecting through experimental investigations on our own. And so through that, we will be developing the first framework, let's say a first draft of the new framework that will enable us to create this holistic dynamically responsive living pipe sizing methodology that can be adjusted based on regions, based on use factors. Again, those factors will be defined towards the end of this phase of the project. And once that is established, moving forward, our next step is the strengthening phase, where we'll be testing the new framework across multiple data sets and regions, and further calibrating, fine-tuning, and to make sure that it does deliver our intended mission. And hopefully the final product will be the cohesive new sizing methodology that not only is built from more precise peak demand estimation that is not necessarily just one, but multiple, depending on the controlling factors, but also reliable. Reliable in essence, we want to make sure that every point that Lisa and Ramiro mentioned earlier, from water conservation to public health and preservation, environmental impacts to eliminating construction waste, reducing energy demand or energy burden associated with water consumption or use practices. So creating a cohesive balance across all of those factors as a usable product. So we are somewhat halfway through this process, but look forward to receiving feedback from everyone as we go through and hopefully collectively produce a product that will be well received globally.
Thank you, Dr. Andiroglu. All right, so now we've reached the panel discussion portion of our presentation. I'd like to introduce our panelists to you. Gary Klein is the chair of the ICC 815 committee. Gary is president of Gary Klein Associates and has been involved in energy efficiency and renewable energy since 1974. Since 1990s, he's led the effort to incorporate hot water as a system into the 4 principles of building science. After serving 19 years, the California Energy Commission has provided consulting services on sustainability since 2008, with emphasis on water, energy, carbon, health connection. And in the middle there is John Lansing. He is a leading plumbing designer at PAE Consulting Engineering in Portland, Oregon. John specializes in applying sustainable solutions to plumbing systems and research on international engineering design guidance, and serves on various code and standard technical committees. He's authored numerous publications to the American Society of Plumbing Engineers, the World Plumbing Council, and ASHRAE. And finally, Dr. Andiroglu. He is the leading researcher at the University of Miami. And hold on one second. Missed something here. My apologies. My screen is not. Dr. Andiroglu, would you mind introducing yourself? My screen is not.
Happy to. So Esber Andiroglu, I'm an associate professor of practice in the Department of Civil and Architectural Engineering. with additional appointments in School of Architecture and in Department of Chemical, Environmental, and Materials Engineering. I'm also the director of the Construction Management degree programs and non-credit, non-degree type workforce development programs in construction sector at University of Miami. My primary research and teaching areas focuses on building sciences, environmental building systems, and sustainability focused academic curriculum. Thank you, Ramiro.
Thank you, and thank you again, Gary and John and Dr. Andiroglu. Appreciate you guys donating your time to us today. We did anybody submit any questions through the Slido program? Dan, did you? No, no. Okay. Okay. Well, do you have a question? Okay.
Hear that?
Yeah.
So the ICC 815 standard development, is that an ANSI process that you're going through?
Yes.
Okay, it is an ANSI process.
Yes.
Is there long-term alternative to an ISO, since you're looking at the data from all these different countries?
Yes, I believe that's, yeah,
Okay.
because the intention is to have this standard be applicable globally.
ISO.
Yeah, yeah, and ISO is one way to do that.
Yeah.
We do have a couple questions that came in from the Slido. I don't know if they're from in the room or from online, but we'll go through a couple of these. So to the panel, one of the questions that came in, should we expect the minimum size of water closet fixture drain to be reduced to 2.5 inches given the water use today?
And anyone on the panel can take that.
This is Gary. Do you want to make us video so we can be seen or what?
I will try to do that.
Good luck.
I need Meta's help for that. Let me see.
So I'll start. John, I'm sure you have something to say about it because I know you pay attention to the drain sizing. At the moment, so the short answer is maybe, but it won't happen immediately. Because I think that the big deal at the beginning of our process, what we've learned so far is that the large pipes in the building, the ones that leave the building, not at the water closet themselves, but after all the branches and trunks collect all the drain water and head out. The large pipes are the ones that need to be right-sized long before we worry about exactly right-sizing the water closet itself. At least that's my opinion in the matter. We have so much less simultaneity than the original codes predicted that we ought to fix that problem first. Matters much more in big buildings from the research we've seen so far. John, what do you think?
Yeah, I second those thoughts. So, closer to the fixture, we'll often see a lot of discussion around, 3-inch or 4-inch in terms of the connection to the water closet, right? And there was some research done at the PERC, the Plumbing Efficiency Research Coalition, back several years ago now, kind of comparing the performance criteria of the 3-inch and the 4-inch. And what the research found was that the gradient was actually a bigger factor than the diameter difference. So yeah, closer to the fixtures, I don't expect we will see a significant change in terms of recommended diameters, but downstream, for example, I've worked on a project recently where I had 2 10-inch sanitary drains leaving the building. I don't think we're going to see that anymore. If you look internationally, based on what recommendations are there, a lot of parts of the world, you'll only see a recommendation large as 6 inches for a sanitary drain, even if it's serving several hundred units of apartment buildings. So it's just never going to fill up, especially given today's water efficiency that was just not accounted for back when those recommendations were first developed.
So John, the other way I look at that question, the way you've raised it is that fixtures themselves are binary. They're either on or off. They can't be simultaneous with themselves. And all of the rules that we have for sizing water piping are for the right sizing, are for the sizing of the branches and mains where lots of fixtures are connected to it, 2 or more. And so this is the simultaneity question that you came to that allows us to do a much better job of right sizing the big pipes. The fundamental questions that we have to make sure we have correct for any given drainage pipe or any given water supply pipe is that are we at the end of the system, what I would call the twigs, the service of one fixture either in or out. That question is a physics question. Do we have enough diameter to handle the volume properly? The right pressure losses, the right velocities, all of those kinds of questions are a different question than the right sizing question that was originally worked on in 1940 by Roy Hunter, right? So we have 2 questions that need to be answered. One is the fundamentals for a given fixture. The other is what's the probability of simultaneity for the rest of the building for all the fixtures as they collect and combine. So this is the hunt we're on. Esber, what do you think?
Yeah, I think you summed it up well. And to follow up from where you left it off, Gary, so that the twig sizing, as we noted, the physics of that, is simple to do for that sizing. However, what happens upstream before we get to that twig and how the peak demand is understood and how the hydraulic properties of that distribution network is understood and how it translates into the ultimate pressure losses at that twig location is really what we need to establish before we can then say, okay, we can size the twig differently. So I think, yeah, we cover this. We're all on the same page, and our collective mission, I think, is to exactly identify the response to that question.
I think the hydraulics question that you're raising is a fundamental one. As we've discussed in the past at other events, the pressure at which a shower head's flow rate is rated, Ramiro mentioned the testing that he used to do in the past life, where we look at these sorts of things. Shower heads are rated at 80 PSI. Faucets are rated at 60 PSI in the manufacturing method of test. These are published standards. Everyone follows them as an industry, and that's how we live. The plumbing codes in the US don't allow more than 80 PSI to the first fixture in any building if you're following the plumbing code, which means the second floor showers can't get 80 PSI ever. And above that, it's less possible each time you go up a floor. And so we have numbers in our codes about the residual pressure for performance, minimum residual pressure for the correct performance of faucets and showers and toilets and urinals and things. And I'm pretty sure those numbers were published before we had modern shower valves and modern flow rates that were published in the 90s or the 80s, right? That number comes from a long time ago. And I think we need to revisit that number for making sure we actually give the performance people are expecting so that our hydraulics are designed correctly. It's one of my pet projects, as you know. What's the pressure loss to an elbow? I don't know. It depends which elbow you pick. And so we don't have numbers for modern faucet, modern pipe materials at all. And we need to fix all of that. That's part of it, but that's not the fundamental piece of 815, which is looking initially at the simultaneity question. I think that we should not avoid the question of what happens with the twigs, either going into the fixtures or coming out of them. We should start figuring that out as well. Do we have any other questions that came in? We spent a long time on one of them, but let's go to another one.
Yeah, we have another question. Actually, there's two questions that are quite related, so I'm going to read them together at the same time. And I certainly think we've talked about this already, but it would be great to get the input directly from the panel. So combine these two. Are there concerns with how new water efficient fixtures will affect the drain line carry for existing buildings installing new fixtures? And another comment question, less flow equals less scouring action equals solids not moving through the waste system.
We have, you are correct. We've sort of been talking around that set of questions. So John, you mentioned the PERC studies that we did here in the US. Do you remember that there was actually one done in Australia, I believe, before we did them in the US? And all three
Yes.
studies found out the same thing. What was the first most important factor?
Gradient.
No, that's the second. What was the first? Toilet paper.
Oh, yeah. Got the contents
Okay.
flushing.
Right. And so it turned out that I forget what that's called exactly, but the tensile strength, the wet tensile strength of the toilet paper was the single biggest factor in whether or not stuff didn't make it down the 3 or 4 inch pipes at any gradient. The second most important factor, the one we can do something about in terms of a plumbing code, quite frankly, or plumbing design and standards, was the slope. And diameter for the two cases they tested, 3 and 4 inches. I'm not sure. I guess it was 100 millimeter in Australia. I'm not positive what the exact test was. Roberts might be able to weigh in on that.
I think it was
But
100 millimeter 4-inch.
Right. And so in all those, the factors after that were almost insignificant. The one factor we have control over is slope. And so go ahead, Esber.
No, I was going to ask Ramiro if he could pull up. He had a slide that showed curves between that represented the vents and the flow rates on the waste systems. If you could pull that slide up back, Ramiro, that would be a great talking point in response to this question as well.
I will try to do that, Esber.
If you can roll
Well,
back, you'll appear. You know, the one that has multiple, it was a Harriet Watts study with the multiple curves.
While he's working on that, finding that slide, I can throw in another question here that was asked. Maybe we can
Go
talk
ahead.
about it while he's looking for that slide. So the question came in, is it fair to say that an existing building would be better served by incorporating water reuse options instead of new water efficient fixtures?
Well,
That's
yeah,
not
that's
obvious.
a very loaded question. And first, you know, existing buildings, you know, depends on the state, the condition of that existing building. When the building may be existing, but what is the state of the plumbing systems, for example? You know, what's the age of the building? You know, what's the age of the piping in that building? Has the building gone through any kind of change of uses or occupancy type during its life? So I would not say it's always going to be one or the other. We're actually currently together with ICC investigating benefits all of these can produce, whether it's the more efficient fixtures or you know, gray water system integration, and it really varies. You may have opportunities to do all, or in some instances, depending on also the budget and the extent of renovation scope. Of course, changing fixtures with new higher efficiency fixtures is a pretty low cost measure in my mind, because it doesn't often require repiping. or significant amount of repiping within concealed spaces. Whereas some of the other measures may involve significantly more work. Again, if a building is going to go through a change of use type renovation or major like level 2, level 3 type alterations, that's when it may be a totally open canvas. What do you think, Gary?
I think that the question is asked, as you point out, is loaded. So let's go through the question as it was. Water reuse means taking something that was created, usually on the waste side, and reusing it for some purpose, either on the supply side in the building or a supply side that's not a potable water use, could be in or outside the building. In both cases, it takes the water away from the final drain pipe that's already in the building, because we're taking it out of the waste stream and putting it somewhere else. And so that's potentially going to create issues on the furthest downstream pipe that goes from the building into the sewer system of the community, or wherever that goes. If we're choosing to use it back inside the building, we have to create it, we have to get it connected to the things it can be used for. And unless we're allowed to treat it to full potable reuse, we now have to separate the plumbing or find a way to use it. So if you have, for example, in an apartment building, all the washing machines are in the basement near the main drain, it'd be pretty easy to create a gray water system of reuse, capturing water that's coming down the drain and using some version of treating it and then reusing it for the washing machines. That sounds like a possible thing to do without too much trouble, because we could separate out the plumbing. But if we can't separate out the plumbing, we're sort of stuck. As you pointed out, only certain levels of renovation in a building give us access. The dilemma we all face is that the choice of fixtures is regulated at the federal level. The flow rates for faucets and showers, toilets, and urinals is regulated at the federal level. And technically, we're not allowed in the US to buy stuff that doesn't meet federal rules. And as we've pointed out, all of our plumbing is rather old in comparison to those changes that were made in the 90s. Any building that was, even buildings built today, are still using rules from pre-1990 flow rates. So we're sort of stuck in this dilemma of how do we best accommodate the next building we build or the next one we renovate. And so I think that the work we're doing in our committee is critical to help give better guidance as to what the size of the big pipes needs to be and what the slopes need to be. I have an issue I want to go back to briefly on the slopes. Both of the US model plumbing codes have an exception in them that says if you don't have enough height for slope, you can go from a 1/4 inch per foot or a 2% slope down to an 1/8 of an inch per foot, or 1% slope, right? And the drain lines, that's all well and good, except I think all new construction shouldn't be allowed to do that. I think we have to design our new buildings so that we make sure we have 1/4 inch per foot slopes, no exceptions. That's an architectural decision more than almost anything else. And I think we have to get architects to understand that the buildings we're building in the future have to be built and designed a bit differently than the ones in the past to avoid some of the problems we're seeing.
And that's a really good point, Gary, because if you look internationally at recommendations, you do find steeper gradients than 1% are often used for the 4-inch diameter drains. And there's a really good question posed about the gray water separation and the performance concerns, because I think everyone's has realistic concerns about that. If you split the water closets off onto a separate drainage system without any supplementary flows from showers, washing machines, or lavatories, and then you put all of those other fixtures on another drain without changing any of the design and installation criteria, how well is that drain with just the water closets and toilet paper flushed down? how well is that drain really going to perform if we aren't changing the way we're designing and installing that? And back to the gradient question, I think a system with too many of those water closets and without any supplementary flows from what we've seen could experience some issues if sloped at a 1% gradient. Another recommendation that you see in a lot of other countries is a rather than a requirement on loading specifically, drainage loading, you'll see a scouring force requirement of 2.5 newtons per square meter. Basically, the intended force of the drainage capacity and the drain, and that often requires some fairly steep gradients to achieve that. And if we look at the fixtures that we're installing today in the US, 1.5 gallon per minute shower heads and 0.5 gallon per minute public faucets. Those are actually exceptionally low flow rates from an international standpoint, yet our drains are exceptionally oversized from an international standpoint. So we really need to be realigning those diameters, the gradients, any other factors, including the amount of bends and elbows and possibly cleanouts as well, to really be aligned with what we're installing in buildings today.
So I think we've talked about drains a lot. Let's talk about some other things. Let's move on to vents for a minute. Esber, when we were at the drainage testing tower in England, one of the most surprising things was the attention they were paying to the vent diameter sizing, and how they were really focused on that. And that to me was an eye-opener. What was that relationship that we saw earlier? 8 to 15 times the flow rate compared to the water flow in the drain. Is that about right?
Yeah. Yes.
And so the biggest thing I learned there was that we need to pay a lot more attention to the right sizing of our vent stacks, like right away. We could fix that problem almost overnight. It's not a fundamental problem of saying, yeah, we should do a better job on it, because we're already doing a lot. But that turned out to be really fascinating to me. The other piece that I saw, John, you weren't there, but Esber, we were watching it. The problem of the lack of simultaneity in the basement from the 40-story tower. They were running experiments for us showing all the fixtures upstairs on the various floors and heights being flushed at essentially the same time. And there was like nothing going on in the basement pipe. You could see it. It was an open, clear, 4 to 6 inch diameter pipe. And there was no peakiness. That was surprising, wasn't it?
Of course, yep. So,
and the peakiness referring to the pressure differential within the drainage system, which of course has to be maintained within 2 inches trap seal variation.
Right. So they were not overflowing the drains or sucking them dry. They could do that. They didn't choose to for some of the experiments we were watching, similar to what we saw in Switzerland, John. You could make it happen or not, depending on what you chose to do. But maintaining the trap seals throughout the building, particularly on the bottom floors, which is where the problems occur with this overpressurization. What I was describing was the peak flow in the main pipe never got very big at all. It rarely even got close to half, ever. They were flushing everything, and it just wasn't showing up as a peak in the basement. I think many of the folks on this call and in the room have heard about the tests that are often done at a new stadium to make sure that everything will work properly when everyone's loaded up at halftime, right? And so they get all the Boy Scouts and Girl Scouts out, and they have phones where everyone's going to flush the toilets at the same time, flush the urinals at the same time in all the bathrooms. And it turns out, and so they do it, and usually the building passes. But it's not a drainage test for simultaneity. That's actually a water supply test. Because if you flush everything at the same time, you're causing a huge peak, an unlikely, highly unlikely peak, by the way, in the 99.99 percentile on the water pipe that's coming in. But to create the same problem on the drainage, the folks at Harriet Watt were explaining that you actually have to have the first toilet flush and then the second toilet time so it flushes exactly when the water from the first reaches it on the branch, the third, the fourth, the fifth. They all go to the stack, and then you go down to the next stack, and all the toilets on that stack have to be timed to hit that stack at the same time the one from above hits. And that probability, well, I'm pretty sure we could all bet on the lottery and win a whole bunch of times before that would actually happen in a tall building. That's the only way to create the huge peaks.
So they're not going to combine at the same time in the drain system.
Correct. And you know, what else is highlighted in what Gary just described here now is that the hydraulic performance, or the hydraulic parameters that contribute to the performance of these systems are not the same for supply systems and the waste and vent systems. So, that's why, we all recognize and agree that these hydraulic performance parameters need to be understood and better investigated, but not necessarily following the same path on the supply and waste and vent side of things.
They're related for sure, but they're offset in time.
Yes, they're not in sync. One of the things I was going to point exactly on the curves that I mentioned earlier on that slide was to kind of exemplify through the curves this point, and how often the unintended consequences we talked about are often misinterpreted or lost, that they can be experienced. However, they can be addressed without sacrificing sizing efficiency in both the supply systems as well as the waste and vent systems.
Right. So let's move on to water supply piping for a little bit, because it's the third leg of the stool we're working on, and it's certainly got issues that need to be discussed. I'm looking at some questions that we posed a week or so ago. I don't know if there's any new questions that have come up in the chat. If there are, we'll take them next. There's one about the timeline of our research. We should talk about that a little bit.
Hey, Gary.
What? Yes, go ahead, John. Go ahead, Ramiro.
There's a question about, with the smaller pipe diameters will result in higher velocities. Will water hammer be a concern? And, will you have to put more water hammer arresters in the system?
That's a great question. So,
well, I mean,
when we
ask that question.
Go ahead, Esber.
Before you answer, Gary, to ask the question, just because we're saying smaller pipe diameter, we're also saying a smaller pipe diameter for smaller rates of flow. So we are not keeping the same rate of flow and just reducing the pipe diameter.
Right.
But go ahead, Gary. Sorry.
Right. So that's the track that needs to be discussed from the logic point of view. Let's imagine the flow rate's 2 gallons a minute. And the current supply pipe, we're not going to talk about drain pipes at the moment. This is a supply pipe question. By the way, there are air hammer arresters for vent stacks too that we got to see in England that I think are fascinating. More on that another day. But for the water hammer arrestor case, it's fundamentally a velocity problem, isn't it? So if you have 2 gallons per minute and the velocity in the pipe that you're living with now is a half a foot per second, there shouldn't be much water hammer, right? The velocities are low relative to the diameters of the pipe. And even fast closing valves have lots of room to work with, if you will. If you still have 2 gallons a minute and you go down to, I'm going to be arbitrary and pick a 3/8 diameter tube, your velocity in 3/8 diameter will be 8 feet per second or close. Well, that's the maximum we want to see in most cold water plumbing codes anyway, right? I think that's for most standards around the world. I think it's a similar relationship. We don't want to see much more velocity than that. Well, okay, we still should be safe. So I'm not clear that water hammer will necessarily become a problem. Should we pay attention to it? Absolutely. Go ahead, John.
It is true that, for a given velocity or I should say for a given flow, if we reduce the diameter of the pipe, we are going to increase the potential for water hammer arrestor. And it's an interesting question because, of course, we have a whole lot more quick closing valves today than we have in past decades. And also, this one project that we were looking at here in Portland, Gary, where we have, I believe it's somewhere around, can't remember, I want to say 10 units on a 3/4 inch pipe. And this is units of apartment buildings. That is a unique scenario that has not been typical in the past with a water supply to an apartment building. And what we did with that project is we did provide water hammer arresters at the supply for each of those units, just to ensure we don't have any issues with that. And the water hammer calculations
that's at the pipe going into the apartment. So
right at the apartment. So kind of at the endpoints, at all of the endpoints, we've got water hammer arresters on both the hot side and the cold side. And, as far as predicting water hammer, it's fairly complex series of calculations that it's really kind of unpredictable without an accurate assumption on what the flow is doing where. And for that, we use the water demand calculator for getting those numbers. But yeah, I think it's a very valid concern that definitely needs some more investigation on that. But until then, I would consider water hammer arrestor to be a good friend.
So I think you chose an interesting strategy, John, which is you put one per apartment, not one per fixture. You address the problem by looking at the junction to the apartment rather than every single fast closing thing in an apartment. But I want to explore for a second what a fast closing valve means. When we were young, it meant a solenoid valve, right? So where do those come? Those are in washing machines and dishwashers, is that right? And I remember when faucets used to be more than a quarter turn, like you actually had to wind your hand around a few times to open and close a faucet. Those were slow closing things, right? Bathtubs weren't 1/4 turn open and close for the valve. You had to go around the loop more than once. Those are slow closers. But aren't an awful lot of valves now a quarter turn for faucets and showers? Isn't that right? So those, if they have a lever on them, I think of those as also fast closing because I can make that happen pretty darn fast. Esber, what do you think?
No, you summed it up really well, Gary. And another thing to throw in the mix there is today a lot of the smart fixtures where the operation of the valves are also automated. So when in putting that in the mix, but I like again John's idea of one per unit. This again really highlights the importance of understanding the hydraulic performance of the piping network beyond that twig.
Right. We have to know what's going on at the twig, but we also have to know what's going on in every node, because it's the
Every
nodes that
node,
are
and
gonna,
at some point, in multifamily larger buildings, you know, we can also start beginning to treat each apartment branch as a twig
as a node. Yes, it is.
in the system. So
Absolutely.
yeah, there is 815's mission really is to address these points, to better definition or understanding of the hydraulic performance or the influencers of hydraulic performance, from pressure losses to velocity variations, you know, and ultimately all of this does lead to water quality issues.
Yes. So John, based on this discussion, you need to leave pressure taps at every hot and cold pipe on at least one riser in that new building you're building, so that we can measure that question of the pressure transients at that level. Otherwise, your best guess we may never learn whether it was good or not.
Yeah, I agree with you. Unfortunately, the water hammer arresters will be doing their job and preventing that from getting too high.
But we should be able to see the transient.
Yeah, I agree.
So give us the tap. We'll watch the transients, and then we'll see that the water hammer arrestor doesn't let them happen for very long. We'll record in the 10 times a second or something. Yes, go ahead, please.
I have one more question that's come in on the questions, and we do have just about 5 minutes before we need to wrap this up and put a bow on it here. So maybe this will be our last question. A question came in: what is the timeline for implementing these changes? The jurisdiction I work for is currently requiring a 6-inch sewer for a single-family home.
I'm sorry. The timeline is that we have really been involved as a committee for less than just about a year now. Is that right? I think it's almost a year. And we are expecting to have early drafts out by the end of this year, first quarter next. So it's going to take a while, because we're trying to do this not based on best guess, but based on good science. And we want to make sure we don't run ahead too far of what we understand to be the facts. Having said that, there's some really good, compelling evidence about the drain lines that if you reach out to Ramiro after this, or Lisa after this, we'll get back in touch with you, of compelling evidence that 6-inch drains for a single family dwelling are like crazy at some level. And if we don't need 6-inch drains for 40-story office buildings, I have trouble understanding why we need them for a single family dwelling unit. I get confused by that.
Something tells me you couldn't hit that 2.5 newtons per square meter if you ran all of the fixtures and then flushed repeatedly.
So
I bet it would not even hit a quarter flow.
It may be a far stretch even then, John.
Yeah, I just don't see it. So it turns out that our codes go back so far and are based on flow rates and flush volumes that no longer exist, that we have a very difficult task in front of us to change our attitudes, because they're so embedded in the psyche of the plumbing world. They're older than, I'm pretty sure, anybody on the call, although I did see somebody here who was close. He's since left. But he was born about then. So give me a break. He didn't become an engineer till 20 years later, right? And that's the basics by which we do all of our design. So the time frame is a 2-year window, I would guess. I don't want to be too firm on it. I'm chairing the committee, and I don't want to commit to a time frame in advance of what we learn. I think we'll have knowledge as we have things we can share now that sound like good practice. We're working through the science behind all of them to make sure they make sense before we publish them in a standard. That's why we have working with the university. So there you go. 2 years-ish for our process, but I think we can help people on the way who, if you've got a willing jurisdiction, we're willing to help explain to them why some things that they currently have don't need to be there anymore and how to understand making those changes safely.
And to that timeline, I want to add to what Gary just said, that even today, based on your takeaways from this meeting today and everything we discussed on this topic, I think you can start thinking about this and implementing, some of these concepts within your own design or construction or review practices when evaluating, options, when you are looking at value engineering projects, for example. So hopefully this type of a meeting today and presentation enlightened you and opened the door for adopting these concepts into everyday practices and your design thinking and review processes.
All right, we've run out of time. Thank you, panelists, for sharing your knowledge with us today. And I want to thank our attendees here in Columbus at the OAPI meeting and also online. We appreciate you guys joining us. We do have another session next week. It's going to be presented by Tom Roberts. He'll discuss more globally the methods that are being used today. So if you need information on that, just reach out to me. Again, these QR codes are there for you to scan so that you can sign out and start the process to get the CEUs. Again, thank you, OAPI.
You're not sharing your screen anymore, so we can't see the QR code.
Oh, okay, I can see it here. Let me see. Hold on a second. Can you see it?
Yes.
All right. Thank you. I'm trying to juggle many different screens here, so apologize for that. Right. Thank you, everyone.
Thank you, Ramiro, Lisa, so much, Tom, for organizing this.
Thank you.
Thank you.
Pleasure, everyone. Thank you for the opportunity to share.
Bye, everyone.
Bye-bye.
PMG resource team, appreciate you, and